So what is gamma decay? Like atoms, nuclei also have excited energy states. Okay, when a nucleus jumps from an excited state to a ground state, it emits photons, whose energy is equal to the energy difference between the excited state and the ground state. So similar to the atom, when electrons jump from a highest excited state to a lower excited state, energy is liberated in the form of photon. Here too, in the case of nucleus, they have to have some excited states and other ground state also. So when the nuclei transfer or jumps from excited state to ground state, they emit photon. This has a range of several mega electron volt and these photons are called gamma rays. The wavelength range is 0.004 Armstrong to 0.4 Armstrong. Now, as an alternative to gamma ray, an excited nucleus in some cases may return to the ground state by giving up its excitation energy to one of the atomic electrons. This process is known as internal conversion. So what is internal conversion? An excited nucleus gives its excitation energy to one of the atomic electrons. Such a process is called internal conversion. The emitted electron has a kinetic energy equal to the lost nuclear excitation energy minus the binding energy of the electron in the atom. Most excited nuclei has very short half-lives against gamma decay, but a very few remains in excited state for several hours. This is similar to the metastable state effect. Since the excited nucleus has a half-life of 2.8 hours, that is an isomer of strontium. Similarly, these two are the isomeric states of bromine. So it may be also noted that an isomeric nucleus has an angular momentum which differs by several units from that of any lower energy state including ground state. So next important section is the cross section. So the concept of cross section plays a vital role in nuclear physics. Most of the information about a nucleus are derived from the scattering experiments. So in scattering experiments, highly energetic particles are bombarded with a stationary target nuclei. The target nuclei present a certain area called its cross section to the incident particle. So any incident particle that is directed at this area interact with the target particle. Hence, greater the cross section, greater the likelihood of interaction. Okay. In other words, the interaction cross-section, which is represented as sigma, is a measure of the effective size of the nucleus for a particular scattering. So it can be thought of as an effective area of nucleus at right angle to the direction of motion of bombarding particle. A reaction will occur only if the incident particle is in this area, sigma. Hence, probability that a reaction will occur is proportional to sigma. So, the probability of any reaction, any nuclear reaction is proportional to the cross-sectional area. That is the importance of this cross-sectional parameter. In other words, cross-section measures the likelihood of a particular interaction. The interaction cross-section of a target particle varies with the nature of the process involved and with the energy of the incident particle. It may be greater or less than the geometric cross-section. Now we have to find out the expression for cross-section and intensity. Consider a slab of some material of area A and thickness dx. If the material contains n atoms per unit volume, the number of atoms in the slab is n a dx. A dx is the volume, n is the number of atoms per unit volume. So n a dx is the number of atoms. Let sigma is the cross section of each nucleus for a particular interaction. Okay. Therefore, total cross section of all the nucleus will be multiplying sigma with this n a dx. If there are n incident particles in the bombarding beam, the number dn that interacts with the slab is given by interacting particles by incident particles equal to aggregate cross section by target area. Okay, so dn by n is equal to na sigma dx by a. or dn by n is equal to cancelling a n sigma dx. Here we supply a negative sign to indicate the decrease in intensity of the incident beam after passing through the slab. This is the incident particle and n minus dn is the particle emerging from the slab. So there is a decrease in intensity of the incident beam after passing through the slab. Okay. So dn by n is equal to n sigma dx. Thus minus dn by n is equal to n sigma dx. Or dn by n is equal to minus n sigma dx. Now, if the incident beam travels through a slab of finite thickness x, then to get the expression for it, we have to integrate the above expression. So, integrating from n0 to n, we integrate this right side from 0 to x. We get n and sigmas are constant. The integration is from 0 to x dx. Where n0 is the initial number of particle and n is the number of particle that emerges after traveling a distance of x. Okay, on solving this you get ln n minus ln n0 is equal to minus n sigma x. Or on solving you get n is equal to n0 e raised to minus n sigma x. Again n is equal to n0 e raised to minus n sigma x. It shows that number of the particle n decreases exponentially with distance. Decreases, negative sign is here. So there is an exponential decrease in the number of particles. Now the cross section has a dimension of area, hence its unit is meter square. Since the size of the cross section is very small, we make use of a smaller unit which is called barn. 1 barn is equal to 10 raised to minus 28 meter square. 1 barn. This is the unit of cross. Next, we can consider the neutron capture cross section of cadmium. We found that cross section depends on the energy of the incident particle. As an example, consider the scattering of energetic neutrons with cadmium 113. Cadmium absorbs the neutrons and becomes cadmium 114 and goes to excited state. While coming back to the ground state, the excess energy is emitted in the form of a gamma ray. This neutron capture is written in shorthand form as CD113 in brackets n, gamma CD114. So, cadmium is bombarded with neutron. It becomes cadmium 114 and after that it goes back to the ground state, releasing a gamma amount of radiation. When neutron capture experiments is repeated with increasing incident neutron energy, it is found that at a particular neutron energy, the cross section is found to be maximum. So this is the cross section. This is the neutron energy. At some the graph is like this. At some particular energy, some particular neutron energy, the cross section is maximum. So the cross section maximum means the number of particles coming out after scattering will be less. That is, large number of neutrons are absorbed. Okay. Moreover, the capture cross sections for slow neutrons are so great that cadmium is widely used in control loads for nuclear reactors. Okay. In the figure below, you can see that cross section becomes maximum at 0.176 electron volt. This is a resonance effect associated with the excited state of cadmium. Next is the mean free path. The mean free path of a particle in a material is the average distance it can travel in the material before interacting. So we know that e raised to minus n dx into dx is the probability that particle interact in the interval dx of the distance x. We can write the mean free path as symbolized as lambda is equal to integral 0 to infinity x e raised to minus n sigma x dx by integral 0 to infinity e raised to minus n sigma x dx. Evaluating this integral, you get it as equal to the numerator is equal to 1 by n square sigma. Similarly, the denominator you get it as 1 by n sigma. Therefore, the mean free path lambda is equal to, substituting the numerator and denominator results, you get it as 1 by n sigma. Mean free path is inversely proportional to n and Next is slow neutron cross-section. It has been found that when slow neutrons are bombarded with target nuclei, cross-sections are much greater than the geometric cross-section of the target nuclei. For example, the geometric cross-section of cadmium-113 is 1.06 bond, but its thermal neutron capture cross-section is about 20,000 bond. The explanation is as follows. The slower the neutron, greater its de Broglie wavelength, lambda is equal to h by mv, and larger the region of space through which it spreads out. Hence, more area of the target it can interact. It can interact with more area. That is why there is an increase in the cross section. Next is reaction rate. It is the ratio at which the scattering process occur in a given sample of a material. Or it is, once again, it is the rate at which the scattering process occurs in a given sample of a material. Let delta n be the number of particles undergoing scattering in time delta t. Delta n by delta t, the reaction rate, delta n by delta t is equal to n0 minus n by delta t. Substitute n as n0 e raised to minus n sigma x. Delta n by delta t is equal to n0 by delta t into 1 minus e raised to minus n sigma x. If the thickness of the slab is very small, n sigma x less than 1, you can write it as the term as 1 minus n sigma x. So I am substituting that term as n sigma x. Delta n by delta t is equal to n0 by delta t n sigma x. Writing this in terms of a flux of the incident beam. Let flux is defined as the number of particles per unit area in unit time. N0 is the initial number of nuclei by unit area, unit time, A delta t. So N0 by A delta t is the flux. So phi is equal to N0 by A delta t, or N0 by delta t is equal to phi A. Therefore, delta n by delta t is equal to phi A n sigma x. But n a sigma is the total number of atoms it contains. Therefore, it is denoted as n dash. Therefore, the reaction rate delta n by delta t is equal to phi n dash sigma.